authentication on the blockchain. Everyone give it up for John.
All right, dude. There we go. So my project, I'm John, for those who don't really know me. My project was Two Factor Authentication using blockchain technology. The basics of multi-factor authentication. Multi-factor authentication assumes that your username and password are not secure, and they're not going to remain secure. So you have a second device that, in theory, is on your person that is able to verify that you are who you say you are. Common examples of this are logging into like a bank's website and then sending you a one-use like text message with a code on it, or an email, or using a key fob or phone app, which is kind of what we're talking about right now. The way it works is pretty basic. You log in on the left side, on the right side of the screen, you have your login page where you put your username and password in. It then sends you, instead of to like the main page of the website, it sends you to another page that has ask for an authenticator code. While that's happening, you use your phone or email or phone app to get an authenticator code that's entirely separate. At that point, you have to type in that code manually. There's no communication between that authentication server and the login server that's asking for the code. The reason being is they're trying to verify that you are actually who you are, that you possess like the phone or the key fob that is giving you that code, and it's on your person. It's a way of verifying you are who you say you are. Quick overview of what I used. I used a lot of Python OS module. A lot of the API calls I made to multichain were just using os.system or subprocess. I used time. I used hashlib for my hashing functions, and Flask for the front-end web pages. OpenSSL was used for all my encryption, and multichain is a Bitcoin-derived blockchain that has some cool features that I took advantage of. So, quick overview of what blockchain is. Besides just cryptocurrencies like people have talked about earlier today, it's a ledger for trades. It records transactions. It stores that data in a supposedly immutable object. It's hashed or it's encrypted, and if you change anything on that ledger, everything gets out of whack and you can tell. So so what I'm using it for is not as a ledger to record transactions. I'm using it for as a database that records immutable objects as the secret messages that are going to derive my authentication code from. Every server that I spun up for this project, and I had 3, act as a node on the blockchain, and in theory, as big as the blockchain can be, the information will always be there and accessible to any of the servers when they check that node, when they check the block. The information I stored on a stream. Stream, basically, when you query the blockchain using the API, it returns JSON object with the information you're requesting. I have an example of that here, what a stream looks like. So on the top is the publisher. It can be searched like a Python dictionary, so it can be searched by the key. It can also be searched by the transaction ID, which is the last line. And the data, actually, you know what? This is a little easier. The data over here is my encrypted secret message. So just like a Python dictionary, you can check the key, you can check the transaction ID down here, and you can search for that data. So that is actually one of the secret messages that I've that's stored on the blockchain that I made. And as it looks right now, there's really no way of telling what it is. So this is actually from the access key, from the access stream, which I'll get into more detail later. So I did a lot of hashing. Hashing is not encryption. Hashing is one way. When you hash something using hashlib, for example, in what I use, you run it through the algorithm, and it is basically infeasible to reverse the process. So once you get a hash out of a given key, that's it. you're in practice, you're practically impossible to reverse that. So I used the SHA-256 algorithm to hash my secret key when I stored it on the blockchain. SHA-256 is kind of a mid-range hash, mid-range function. Bitcoin uses it twice when they encrypt their trades, when they hash their trades. But it is kind of mid-range, and hashing algorithms over time get weaker and weaker as processing power gets cheaper and cheaper. Encryption is a different thing because encryption is made to be reversible. So I use two types of encryption. I used AES, which is a symmetrical encryption, and that is kind of like the old-timey, like I give you a decoder ring and you can decode this message, as opposed to RSA, which is a public-private key, where when something is encrypted with the public key, in which anyone can encrypt something with a public key, only the private key holder is able to decrypt that message. So how I used it was I encrypted the secret message with AES. I encrypted the password that I used for the secret to encrypt the secret message with RSA, and then I encrypted it with the public keys for the recipient servers that I wanted to access that stream. The reason why I did this was the secret message that I encrypted was fairly large, and if I encrypted it with the RSA key initially, since RSA functions slightly different and it just basically does math to the string you're storing, the secret message just got too big when it was encrypted with RSA. So a workaround that was to use AES, which encrypts byte by byte, and it keeps the message size the same. So when you're encrypting a large amount of information, this was the only way I could really get it to work. So I've got a little diagram of how things work. I have my login server, I have the Two Factor Authentication server, which is going to give me my code, and I have my node that writes. I didn't want to give the other two servers the ability to write to the blockchain. It's just more secure not having that capability. They can only read. Well, other than publishing their public keys. Let me see if I get this to work. There we go. So login and Two Factor server publish their public keys. Obviously, they keep their private keys private. After that, they're done writing. The writer node then generates a password and a secret key that's going to be used for the hashing. The password and secret key are hashed together with AES encryption, and they are published to the item stream. At that point, the writer node pulls down the public keys from the public key stream, and it uses that to hash together. It uses that to hash together the password in a way that only those individual servers can see or can read. Anyone can see it, but only they can decrypt it and read the information. So at that point, you have public keys on the public key stream, you have the passwords encrypted on the access stream, and you have the secret message that generates the login code encrypted on the item stream. So now the writer node is out of the picture, and you have just the login server and the two-factor node. And they're both going to run the same processes independently of each other on each server. So there's only one set of arrows here. Initially, both the servers will pull down and then decrypt the private key using from the access using their private keys. They decrypt it. There we go. Sorry. They pull down the password from the access and they decrypt it with their private key. Then what they're going to do is, now they have that password in plain text stored there. They pull down the secret message or the secret code from the access stream, and they use the password to decrypt it. So now they can take that password, or they take that secret message, hash it together with the time using SHA-256, like I mentioned earlier, and that is going to give them a code. And do a little math with that code, and then they can publish. Then the two-factor server will send that to the website, which I can access from my phone. And the other one, the login server, just holds that in reserve and will check after your input. So why we need two-factor authentication? People make bad passwords, make really bad passwords, and they do it constantly. Data breaches constantly occur, and in the wild right now, because of all of the data breaches that have occurred in the last 10 years, there's over 500 million real passwords that people have used that you can check. And there are sites that you can check if the password you're using is on that list, and if it is, you probably should change it. Companies can't keep your password secure. There's hundreds, if not thousands, of data breaches all the time, every year. And even companies that hash passwords, given enough time, those passwords will be cracked. So once something is stolen from a database, it's just a matter of time. And as processing power gets more powerful, that amount of time that it's going to take to decrypt those passwords, it gets less and less. Here's some examples. 2017, we had about 1,400 data breaches. Previous to that, 2016 was 12, 100,000. A year before that, it's getting worse and worse. Facebook lost 50 million user accounts. The Yahoo hack that happened in like 2013 was updated last year to say it wasn't 1 billion accounts, it was all 3 billion Yahoo accounts that were exposed. So even data breaches that happened 5 years ago, we're still seeing the effects from now. And it's a problem that's not going to go away. And if you only rely on username and password, eventually you're going to burn. So, if, assuming a username and password database is downloaded and the passwords are securely hashed, there are a couple of ways to break into them. You can use a brute force attack, or you can use a dictionary attack. Brute force attack basically starts with the letter A, and then does AA, and then AB, and AC, and goes through every possible combination of letters and numbers. It symbols in, and it takes time, but eventually it will happen, and they'll figure out your password. Dictionary attack is a lot faster. They take a list of passwords that have already been used, and they know people have used. However many, 500 million passwords are out there. You can find lists that are gigabytes in size of text files, and they just try those words. They give them rules and say, replace the letter E with the number 3, replace the letter I with an exclamation point. A computer can do it in seconds, and in milliseconds. So we need to have a way to prevent those types of attacks from breaking into our usernames and passwords. Just for quick examples of how things work, if you use a password like QWERTY or password 1, subject to a dictionary attack, it takes 0.22 milliseconds, which is a nanosecond, very, very fast. But if you were to brute force something like that, password 1, it's a 9-character long password. It would take about 2 months. But there's no need, because everyone knows someone who's used password 1 at some point. I decided to try and make something that was a little more complicated to crack. So I used 2 words, byte and room, put them together and inserted random characters in the middle. It breaks up the words, so you can't just combine 4-letter words. And mathematically, it should take about 91 millennia to crack. It's not hard to make a difficult password, or even something that you can't remember. You just have to make it difficult for a dictionary attack. And also, that's 10 characters long, so it does add more processing time. The only way to do that would be brute force. Dictionary attacks will work on that. So, successes that I had: the system works. I get the same answer from both my login server and my phone. I had a lot of difficulty getting subprocess to work with Unix pipes, but eventually figured that out. Learned a lot about how Python talks to the OS. Challenges was, initially I tried to use the Python built-in like PyCrypto, PyRSA. When Python reads things from different places, a lot of times it changes types from like a byte stream to a hex, or hex to bytes, and they don't always work nice together. So I kind of worked it out to just use os.system and do all my API calls basically from the command line because I know they would work that way. Right now, all of my servers calculate time locally. I don't have one server that gives out time for everything, so even though I have my servers update every 30 seconds, it's really like 25 seconds because they're not perfectly in sync. My next steps, I need to add functionality for more users, because right now I have it set up where one account talks to the server and and that server's wallet address is the identifier. So I need to develop a way to access that authentication server from like a phone and have a unique identifier for the phone. And I want to update my hashing algorithms to something a little more robust than SHA-256 because, like I said, it's kind of a mid-range thing. It's not the best. It's starting to get old and show its age. And yeah, and right now I have no countdown timer. So if the site updates every 30 seconds on its own, but if it's out of sync, I don't know it until I get kicked out where it doesn't let me log in. And just a couple of resources. I can send these around if anyone cares. Wikipedia's list of most common passwords. Please don't ever use anything on that list. Multi-chain stream confidentiality is where I got a lot of the information for my blockchain stuff. And the haveibeenpwned.com website is really good at checking if your email address or your password shows up in any of those lists of data breaches. So I could send those around if anyone else cares. And oops. Now for a quick demo, we got a login page, and for this site, I figured I'd use a really bad password. So the username and password are John. And this is all hard to do. So now it's going to ask me for my authenticator key, which is on my phone here. And hopefully I can get this in fast enough that I don't have to do it twice. There. So that'll log me into my site. I made a quasi trading site for demo. But I can show you what happens if you input the wrong code. So I go John and John, and then I put in any 8 digits. It will just kick back to the original login page. It doesn't allow you to log in. So that's my thing. Does anyone have any questions?
What's the app running on your phone?
What's up?
What's the app running on your
It's
phone?
just it's a Flask app.
Oh, that you just like open. Gotcha.
Yeah.
What's used for your website's template?
Oh, there's a site called Creative Tim. It has a lot of like pre-made Flask bootstrap like templates.
What's the name of that site?
Creative Tim. It has some good stuff. So a lot of free things that look good.
Take heed.
Yeah, you still have to buy it. Yeah.
Hmm?
Did you buy it?
No,
Oh, you have
he has
free?
tons of free ones. Just scroll through.
Can you circulate that on Flash or
Yeah.
Discord?
Yeah, I'll send that. And if anyone cares, I'll send the resources that I used. That list if you care about your passwords and stuff. And want to look at it. This is a video.
John,
Good
question.
What's up?
Yeah, just to clarify, the secret key is being pulled from the node's operating system.
Well, the secret key is generated on the writer node.
Okay.
And what it does is basically when you hash together, you could hash together a secret key and get a unique hash from that, but it's not going to change over time. So you want to use something that's either only used once, so you hash it with like a nonce and just get a one-use code, or what I did was I combined it with Unix time that I mod 30, so it only changed every 30 seconds. Not mod, floor division 30. So it only changes every 30 seconds. So it gives you like a window where you can enter that code. And when it's hashed together, it's going to see the same code for 30 seconds, and then at the 31st second, it changes. And that's how like that constantly changes. That authentication code constantly changes. So the hashing is it's really interesting stuff. It's pretty a little bit on the complicated side, but it's definitely stuff that's worth like looking into. Anybody else?
All right, let's give John another round of applause. Last but not least, we've got Adam up again. Good stuff. John and I are going to pop. Good stuff. Great stuff.